Hello there guys, welcome back to another epic and extra maths video. In this video, we're looking at the p-test, okay? The p-test, or sometimes called the power test. What is that? Well, it's written right here. So basically, and we're gonna prove it in this video as well using the integral test. And if you've not seen the integral test, this video may or may not make any sense. So go into the description, click on that link, take you to this playlist, and you'll see all of the integral test videos and it will make so much more sense. Okay, but the p-test is as follows. If you're trying to determine whether this series is convergent or divergent, all you need to do is look at what p is, okay? So if p is bigger than 1, this will converge. If p is less than or equal to 1, this will diverge. That's it. That is the p-test, okay? So for a very quick example, if I wanted to know whether the sum from n equals 1 to infinity of 1 over, let's say, n cubed was convergent or divergent, I would go, oh, that's in the form 1 over n to the p, 1 over n to the 3 in this case. And I would go, oh, well, 3 is bigger than 1, therefore it converges. Convergent, done. That's it. That's literally it. Okay? And likewise, if we had a number less than 1, like, I don't know, a half, then I would be able to look at that and go, that's divergent. Just straight up. Divergent because of p-test. Boom. Done. But why? How do you prove that? I mean, on an intuitive level, maybe it makes sense. And by the way, you could have a negative number there as well, but that'd be a bit boring. But yeah, maybe on an intuitive level, it makes sense. But like, can we prove it? And yes, we can. We have to use the integral test. Okay. So in order to do it, we're going to split it into 3 cases. First case is going to be when p is bigger than 1, and we're going to show that it converges. Second case is when p is less than 1, and we're going to show that it diverges. And last case is a bit different. That's when p is equal to 1. And you might notice when p is equal to 1, we have 1 over n. And that's actually divergent. We've already seen that in the integral test videos. 1 over n is divergent. But also when you do the integral test, you get a completely different thing. You get a natural log when you integrate it. So it's completely different. Anyway, we're going to see all 3 cases, and we're going to show them all separately, and we're going to show the p-test is really cool. So let's do it. So first of all, we are going to show that this will converge for any value of p bigger than 1. Okay, first things first is, as always, because we're going to do the integral test to prove this, what we need to do is draw the function 1 over x to the p. And that will always look like this, guys. At least for the positive values of x, it will look like this. Some notable points on here are as follows. So, yeah, again, this is y equals 1 over x to the p. Obviously, we're going to have the point 1 and then 1 over 1 to the p, so just 1, 1. The next point would be 2, 1 over 2 to the p. Another point here, this is 3, 1 over 3 to the p, and you get the idea. Now, if I was to write out a few terms here, I would have 1 over 1, so just 1. Plus, again, 1 over 2 to the p, plus 1 over 3 to the p, plus 1 over 4 to the p, and again, that goes to infinity. So the height of each rectangle is just these points that I've put in here. So what I'm going to do is I'm going to draw the rectangles in like this. Because I'm trying to show that it's convergent, I want the rectangles to be less than below the graph. So I need to draw them like this. Okay, hopefully that makes sense. Oh, that last one was terrible. Let me try and do that again. There we go, that's slightly better. And again, it goes on forever. And I want to show that the sum of all of these rectangles is convergent. It doesn't end up being infinity. And the reason is because we can say that it's less than the area beneath this graph, which if we choose the right limits, we can show that it's finite. Now, one thing to mention is, if you're an eagle-eyed viewer, you might notice that actually the area underneath the graph from 0 to infinity is actually infinity, okay? Because you have this here, okay? This thing here. The area between 0 and 1, for example, because you have this thing here, we've actually already seen this in my improper integrals playlist, but if you haven't seen that, don't worry. It's infinity. So the area underneath the entire thing is infinity. But the thing is like, it's not, you might say, oh no, that's not very good. But it's like, this rectangle is just one guy. So what I'm going to do is I'm going to be a bit clever, and I'm not going to try and do this like double improper integral. It's improper this way, it's improper because of the zero, there's an asymptote. I'm not even going to mess with that, okay? I'm not going to mess with that. What I'm going to do is I'm going to do the integral from 1 to infinity, and I'm just going to add the area of this rectangle at the end because it's going to save me ages. And you'll see, if that doesn't make sense, you'll see exactly what I'm talking about right now. So I'm going to say, and hopefully we agree, okay, I'm getting rid of the first rectangle. I'm not including this for a second, okay? I don't care about that. I want to say that the sum from n equals 2 to infinity, so I'm starting on the second rectangle of 1 over n to the p, is less than or equal to, and tell me if you agree with this, well, I know that you can't speak, but just in your head, the integral from 1 to infinity, okay, of 1 over x to the p dx. Does that kind of make sense? Because again, I'm not including this first rectangle. I'm not including it. Because if I can show that this converges, as I'm pretty sure I've said in other videos, if this converges, then this converges, because the first term is just the number 1. Adding 1 to something can't make it not converge anymore. If this is convergent, this has to be convergent. There's no way that adding 1 makes a series go from being convergent to divergent. That literally makes 0 sense, as you might imagine. So as long as I can show that this is convergent, I've shown that this is convergent, because this plus 1 is this. Okay, that's the idea. So, and the reason I do it is because this is not good. Don't need all this area up here. Don't need it. Okay, so how do we actually do this integral? Well, guys, as follows. Right, so this integral here is the limit as t approaches infinity of, right, this here, 1 over x to the p, I'm quickly going to replace 1 over x to the p with what it also is equal to, which is x to the power of minus p, okay? It's the same thing, but now we can integrate it a little bit better. We're going to get x to the minus p plus 1 divided by minus p plus 1, and that's being evaluated from 1 to infinity. Amazing. Okay. I'm going to come down here. And then I'm going to plug in, well, I say infinity, I should actually have that as t, shouldn't I? And I'm going to plug in t and 1. So I'm going to go t to the minus p plus 1 divided by minus p plus 1 minus 1 to a bunch of stuff, doesn't matter, still 1, divided by minus p plus 1, like that. Now, we have already said that p is a number bigger than 1. So we have minus something bigger than 1 plus 1. This number here is negative. Does that make sense? I hope that makes sense. Because it's like, if it's bigger than 1, then p might be like 1.5 or 2. And then we have minus 1.5, minus 2, whatever it is, plus 1. That's negative. So as t goes to infinity, we have t to the power of a negative number. That goes to 0. Okay? So this ends up being equal to minus 1 over minus p plus 1. Okay? Which can also be written as 1 over 1 minus p, if you want to be a little bit better with it. Or actually, my apologies, not 1 over 1 minus p. It would be 1 over p minus 1. That's actually what I mean to say. Okay, in any event, it doesn't actually matter what that's equal to. I hope that we can see this is convergent because p, we've already said p is bigger than 1, so that can't be infinity either. It's a number bigger than 1. So that shows that this series, for when p is bigger than 1, definitely converges. Hopefully that makes sense. Okay guys, now we're going to do the exact same thing, but we want to show that this is divergent. So it's the same sum, but this time p is a number smaller than 1. So it could be a number that's still positive, like 0.5, or it could be a negative number like minus 50 or something like that. Anyway, whatever it is, if it's less than 1, this will diverge. So how do we show that? Well, we're going to draw the exact same graph again, but this time I want to draw the rectangles such that they are above the integral. Okay, so again, it's going to be the same graph. Again, this is y equals 1 over x to the p, like that. And we still have all of the same notable points. Okay, so very quickly drawing these in, we have 1, 1. we have, this would be 2, 1 over 2 to the p. This would be 3, 1 over 3 to the p, etc., etc., etc. If we were adding this stuff up, it would still be 1 over 1 plus 1 over 2 to the p plus 1 over 3 to the p, etc., etc. You guys get the idea? And then if we were to draw in the rectangles, again, I want to draw the rectangles so that they are bigger than this graph, because if I want to show that something is divergent, I need to show that it is bigger than something that is also divergent. So what I'm going to do is I'm going to draw the rectangles such that they all come like over like this. So this is the first one. This would have an area of 1. This one here would have an area of 1 over 2 to the p. This one here would have an area of 1 over 3 to the p, etc., etc., etc. And again, this just goes on and on and on forever. Okay, now this one hopefully is even more intuitive because we don't even need to worry about a rectangle here because we've moved them all over. So do we agree? I hope that this makes sense. Can we say that the sum from n equals 1 to infinity of 1 over n to the p, and again, this is when p is less than 1, this would hopefully clearly be bigger than or equal to the integral from 1 to infinity of 1 over x to the p dx. Can we agree with that? Just by looking at it. So all we have to do is show that this integral is divergent so that we can say that this is bigger than or equal to infinity, therefore this is divergent. That's the nature of the integral test anyway. So we've already done this integral, so I'm going to absolutely blitz through it because we've literally just done the exact same one. So it's the integral from 1 to t, as t goes to infinity, of x to the minus p dx. Okay, this is the limit as t approaches infinity of x to the minus p plus 1 divided by minus p plus 1, like that, from 1 to t. Okay, now this is where it gets a bit more interesting and different to last time. We still plug everything in, so we have t to the minus p plus 1 divided by minus p plus 1 minus, again, 1 over minus p plus 1, like that. This time it's different. We've already said that p is a negative number, okay? So now we have, and when it's, or not, I shouldn't say negative number, a number less than 1, okay? Because p is a number less than 1, let's say 0.5 or something like that, we would have t to the power of minus 0.5 plus 1. That's a positive number. In fact, minus anything bigger than 1 plus 1, or anything less than 1, sorry, I'm getting them all mixed up, minus anything less than 1 plus 1, okay, that's going to be a positive number. So as t goes to infinity, this diverges. So this is divergent. This is divergent. Hopefully that makes sense why. Because we're doing t to the power of a positive number here. And because it's divergent, the series is like bigger than infinity. So this series from n equals 1 to infinity of 1 over n to the p, and again, when p is less than 1, this is bigger than or equal to infinity, therefore it is divergent. Okay, so that's 2 out of 3 cases proven. Let's do the very last one. Okay guys, the very, very last one is when p is the number 1. Okay, now again, we're going to draw the exact same thing one more time. So it's just going to be the graph of y equals, in this case it's just y equals 1 over x, because we actually know the exact number that p is, it's 1. So we just have this function here, and then we know a few important things here. This one's quite easy because it's just 1, 1. If this is 2, then this would be 2 1/2. This would be 3 1/3, etc., etc., etc. Okay, and we're going to use the integral test again. And again, we want to show that this is divergent because it's right there. So how do you show that it's divergent? Again, we've got to draw the rectangles such that they are bigger, they occupy more area than the area underneath the graph. Okay, so on and so forth. So this is the value of the sum, okay, when p is the number 1. So it's basically just the sum, you know, again, 1 over n here. And we're going to do the integral. So can we agree that the sum from n equals 1 to infinity of 1 over, and I'm just going to say 1 over n now because p is the number 1. This here would be bigger than or equal to the integral from 1 to infinity of just 1 over x dx. So it's the same setup as last time. However, the working out for the integral is different because obviously this is going to end up being a natural log kind of situation. So this here is the limit as t approaches infinity of the integral from 1 to t of, I'm going to leave it as 1 over x dx. And this is the limit as t approaches infinity of the natural log of the absolute value of x from 1 to t. And we can see here, when we plug everything in, we get the limit as t approaches infinity of the natural log of t minus the natural log of 1. And I'm abandoning the absolute value signs because everything's positive. The natural log of 1 is 0, not that it even matters. The bigger issue, it's pretty useful if we're trying to actually prove it's divergent, is the natural log of t as t goes to infinity, that's infinity, okay? Because basically the natural log of t, just the graph of it just increases without bound. There's no maximum value of the natural log of t. The natural log of infinity is infinity, if you want to be casual with it. So this is infinite, okay? And so as a result, basically what we're saying here is that the area from 1 to infinity here is infinite. And because the area of the rectangles is bigger than that, then that's also infinite as well. So that means that the sum from n equals 1 to infinity of 1 over n is bigger than or equal to infinity again, so this is divergent. So just as a summary of what we have here, again, this sum will be convergent if p is bigger than 1 and divergent if it's less than 1 or equal to 1, now we know. So what you can do to finish this off is you can basically evaluate some sums really, really easily just by looking at them, okay? Just by looking at them, you can determine whether a sum is convergent or divergent. For example, if we had the sum from, let's say, n equals 1 to infinity of, let's say, 1 over the square root of n, is it divergent or convergent? We can just look at it because we can rewrite this as the sum from n equals 1 to infinity of 1 over n to the half, because that's what the square root of n is. And again, guys, by looking at it, we can see that because 1/2 is less than or equal to 1, this will diverge. So this is divergent. And this is really useful. You might say, oh, it only works in some pretty specific situations though, right? Because it has to be of like, basically of this form. What we're going to see in the next video is, no it doesn't. We can actually do some really cool stuff with this. There's something called the comparison test, where we can look at other things that look a bit like this, but not exactly like this, and we can use the p-test. So if you're thinking, oh, it's a bit useless, actually it's not. So in the next video, we're going to see that, but hopefully this, it's pretty simple how to use the p-test, I hope, as long as you know what numbers are bigger than other numbers, which, come on, we all do. Anyways, guys, as always, thank you so much for watching. I highly appreciate it, and I'll see you in the next video. Cheers.